Well, I'll start by, of course, thanking the organizers who put together a great program. I do think they made one kind of mistake, and that was asking me to talk. I will contrast what I'm going to say to what Karsten presented yesterday, which I thought was a very beautiful introduction and really had a lot of the, how we want to move forward in the workshop. It really, I think, hit upon a lot of the key things, like going beyond the computational hydrogen electrode, going beyond potential of zero charge, having screening with implicit solvent and then explicit, doing sampling with machine learning, coupling to mesoscale. I mean, it's all the things you want to hear. And here I'm going to say none of that. I mean, I think I'm back in the, Carson showed this famous paper by Norskov and Rossmile where there's like 6,000, some thousands of citations for it. And I think I'm in that bin of people who are just sort of old school. And, I really like these descriptors that you can have. And so I was kind of thinking about it last night, like, why is that? Because it's not like we're kind of scared of doing a complicated simulation. I think it more has to do with, if we're really working with experimentalists and trying to understand experiments, and as I'll try to explain here, sort of our story of trying to predict new catalysts, I think there's a lot of power in a simple model. You can definitely make any model more complicated. You can say you want to do ab initio sampling of a reaction path or something, but I think we do have to ask, if you're going to put that work in, what's the benefit? Where is that kind of a description really needed? And I think that's where I'll try to challenge people in terms of where simple descriptors really have worked in the past and continue to work, and where you need more. And it's a little weird for me to say it because, I'm a dynamics guy. I love to calculate barriers, but I feel, and this is what I was thinking, I was trying to put it into words what I was thinking about in this meeting, and I think it's a little bit different with electrocatalysis. So in contrast, when you're trying to do gas phase or just know the dynamics of a system, I think the barriers you encounter can be very important, and finding reaction pathways and mechanisms from calculations can really inform what's going on in an experiment. I feel with electrocatalysis a little bit different, and that's because I think they really have very good control over individual steps, and particularly when there's an electron and a proton coupled reaction, an electrochemical step, they can just adjust the potential. Like if there's a big overpotential, they just up the potential by 0.1, 0.2 volts and see when it turns on. And so to me, I think it's much more natural to compare overpotentials. I mean, I know it's kinetics, but I think there's a very strong correlation between binding energies and overpotentials. And so in a lot of the examples that have come up where kinetics are important, I sort of go back and think, there are good descriptors based upon binding energies often. So Karsten mentioned like peroxide formation on noble metals like gold as a puzzle. I don't think it's a puzzle, actually. I mean, if you just look at OH binding is very weak on gold. It's not going to split the OO bond. It's going to go the peroxide route. And I think, another example that came up is like OER and OOR. And there, kinetics is a big thing. I mean, you really can't avoid a 0.3 overpotential either way, ORR or OER. And I think that, Norskov and coworkers did a very good job explaining that. The strong correlations between oxygen binding, OH and OOH. And you really can't get rid of a 0.3 difference between two of those. And that's why in a fuel cell, like you'd like to get 1.23 volts, we have no catalyst that does better than 0.9, even high loading of platinum. OER, we can't do better than 1.5, with iridium oxide. And so it's a very simple model, and it kind of explains things. So that's why I feel like an old curmudgeon here. Like, I know we want to move forward, but I think it should be motivated by questions we want to answer. And so, anyways, with that very overly long introduction, I will tell you about, sort of our sort of basic crude approach for trying to model catalysts, and particularly electrochemical systems. And some successes and some challenges. And what I'll try to distinguish between are things that I think of as sort of not simple, but where the sort of classic Norskov models of using descriptors like binding energies and how properties change with binding energies, or how the function change smoothly with properties. It's sort of what you'd really like. It makes it easy to predict things. And I'll contrast it to some cases where we've tried to make predictions and properties can vary wildly with composition. So it's going to be some anecdotes and just sort of our story of how we've done it. But again, I just sort of apologize in the sense that it's not really in the spirit of the meeting, which I told the organizers. This is back, and so Richard said, fine, we can have a bit of a counterpoint, but that's all I got in terms of how we model things. Yeah. And again, we really are just trying to understand experiments and make predictions with the simplest models we have. Oh, one more comment. Let me think. There are some of these approaches that, like Karsten described, which I think are very good. And easy to use. So, Richard's solvation model is great for screening. Going beyond potential zero charge is sort of an easy thing to do, and we certainly do that. Applying a constant potential. We have no fluctuations, sorry. We're not sure they're important. But we're not sampling energy barriers, for example. I don't think that's really important for what we want to describe. Feel free to jump in if I'm saying things that you don't like. Or okay, we're all on the same page. Okay, so with that,
Sorry, but at some point we really need to discuss about that, perhaps not now, but just want to say, to voice my objection.
Good.
What you say is all true, of course, yes.
Oh, okay, we're done.
But is it enough? That is my question.
Sorry?
What you say is all true. Energetics, for sure, is important. And you cannot go below that. The overpotential cannot be lower than the one determined by the energetics, but is that enough really to understand what is going on? That is.
Yeah, and I put it the other way as a challenge to the group. Where do you really need it? So the ones I've heard about.
Selectivity.
Sorry?
Selectivity.
Yeah, so when it comes to so there's another one, I didn't mention it, but CO reduction. You can do very good with CO binding versus hydrogen binding. For reduction of CO2 versus HER, which is one of the key challenges there. So I guess I just want to know, what is the example where there's a real puzzle where you really need these sophisticated methods that answers a scientific question that I can't do with a descriptor?
Zeroth order approximation, you can only do a descriptor if you have a reliable structural model of your surface. An FCC 111 surface is not a reliable structural model for a working electrocatalyst.
So for that, I completely agree. And in fact, this is one thing I'm going to focus on, is that most of our effort here really goes into structure and stability and not on sort of a fancy model. It's very basic, but that's where we spend a lot of our time. I totally agree with that.
The problem is that the structure evolves under the applied potential.
I totally agree.
Therefore, there's what you call the fancy pants methods. You need them also for the structural sampling. At the moment, we can't do it yet because it's too complicated. We're working ourselves off of the electrolyte. But eventually, you need to combine this to lead to a proper structural sampling and get an understanding of what your working surface looks like.
Well, I'd push back a little. So I'm totally in favor of applied potential and a Porbet diagram to know the surface. But I'm not sure about ab initio sampling of water or even machine learning, whether that's important or not. I'd like to see an example.
But let's see, if you go into corrosion, which is very similar, then really two structural things.
No, catalysts.
Yeah, but catalysts, so what Carsten knows. How do you really modify your surface under these conditions, under realistic conditions? It's degradation of your catalyst. So that's what you have really. So we are talking about the working catalyst also. You cannot really assume that the surface will always.
So I'm going to focus on an actual catalyst. If your catalyst breaks down, it's not a catalyst.
Every catalyst breaks down.
I know, but it has to be stable over a time scale where you're doing.
Corrosion is unwanted catalysis.
Yeah. Well, no, catalysts have to get back to where they were.
I mean, if you see the paper of Noskov, it has, of copper, it has a cycloglutammetry on ideal platinum 111, and what you observe at the end, it's a stepped surface. And if you look at the activity of a hydrogen evolution, it comes from edges because it depends on edges concentration.
That is all within what I'm talking about.
That is not complete, absolutely.
There's no kinetics in that, what you described.
Who knows?
Okay. I mean, you can find it stepped with a Pourbaix diagram, and you can look at activity based on descriptors from those steps versus the faces.
If they are enough.
And again, that's why I'm coming back to the group and saying, where do you need more?
Okay, so
Yeah.
I think
Because
everywhere. But
mere observation doesn't help. You need to understand mechanistically what's going on in order to come up eventually with better catalysts.
Yeah, and that's what I hope I can. That's one thing I love about these simple models, is that they very often provide guidance for design, whereas a very complicated ab initio sampling to give you some barrier doesn't.
I agree in parts.
so we are
The point
getting
is,
there.
I mean, you have to validate the cheap descriptors. Right? So at the end of the day,
Yes,
we want to
yeah,
condense
that's right.
everything into simple models because we want to understand, and that's the guidance that we want to have. But you have to make sure that these descriptors are actually guiding you in the right way. And that's why you need very sophisticated things to actually check on this and condense good descriptors.
For that, I completely agree. Yeah, you can't just rely on them.
We
Yeah.
love each other, I know.
You-
Yeah, it was in a similar spirit also. So what you assume is so that you know already what is the initial state, what is the final state. That's what we really in corrosions, we came up then with products nobody had really thought before. This really came out only really in doing then the full calculation, so that we were, it's, of course, so one thing really to say, I know, let's say it's the initial, final, this is then where my equilibrium is. It was really so that everybody in corrosion was thinking, so you are getting essentially dissolving metal atoms. What really came out was then a magnesium OH minus type of complex. For 150 years, nobody had really considered this as a possibility. And this is where really, for this type of qualitative new insight, I don't really see so there's a way around, and I fully agree also in the end. We should come back then to some kind of simple description. It was only that we had this complex description in order to say, oh, it's so simple, everybody should have known. But I think this is really where this type of, let's say, fully fledged calculations can shine if you come up then with something qualitative new insight, where you later say, you just
Yeah.
need
I just
a
want to
sheet of paper.
point again to the, we're talking about catalysis here. And so the experimentalists know what they get. They know the products, right? I'm not talking about corrosion. And in fact, things that are like, irreversible and you just want to know dynamics over time, I love that problem. I just don't think it's an electrochemical problem. Corrosion is not really, I mean, we talked about this briefly, but this is about going past the surface, corrosion.
But it's electrochemical, because you really change.
Okay, I won't
charge
push that.
state.
I won't push that line too much, but it's not catalysis.
Okay, good. We have still, yeah, 2 more months to discuss
Yeah.
these things.
Okay, so what we basically do is we work with experimentalists, and we have this sort of cycle that you see in a lot of papers on materials discovery. I think it usually starts with synthesis, in the sense that you have to work in the sandbox of where the experimentalists can make something. And I think oftentimes a new catalyst is really a new synthetic method where they can make something cool, and then you have to characterize it and test it, and then you want to make a model where hopefully you get the right structure, and that's, like Carson said, a big challenge. But if you can, then you can make some predictions and hopefully guide new synthesis, and this is the dream of accelerating materials design. And like I said at the start, sometimes it works smoothly and things just work out, and a lot of times it doesn't. Like, you make predictions and then it's different in experiment, then you have to go back and find, do the experimentalists have something different than what they thought they made? Is your model too simple? And so you have to iterate like that. Okay, so one example that I will use and that we've modeled is this oxidation of hydrogen or burning hydrogen like in a fuel cell. And if you were to do this and get all the energy out, you get this 1.23 volt, 1.23 electron volts per electron. It's a 4-electron process. And when we think about catalysis and an efficient catalyst, really what you'd like is the flattest sort of landscape here. Because if it's flat, your reactants would come in and form products and you get all the energy out. But it's never really like this because you have chemistry. So you have things that absorb. This is a cartoon, but you have things that absorb. You have to break bonds, and so that hinders this reaction. And what I've sketched as a cartoon are kind of two extremes. If you have something like a noble metal, so you take gold and you try to do ORR on gold, you're kinetically limited. Things don't want to interact with gold, and it's very hard to break barriers. And so you need a high overpotential to drive it. And in the other extreme, you could say, well, I just want to go to something like iron or cobalt or whatever, because the barriers will be lower and it'll be easier. But then you have the opposite problem where intermediates or products will bind to the surface irreversibly, and then you have to somehow drive them off. And so neither one is really ideal. And a lot of catalysis is really about sort of the Goldilocks, like you want to have a trade-off between the two. And so, I've drawn this, but this is actually a pretty good, I think it's characteristic of how energy landscapes change with materials when they're changing in a smooth way. So if you go across the D block, for example. And one thing I want to point out here is that as you change your metal, there can be correlations between barriers and binding energies. So they shift in a concerted way typically. And the reason for that is, this is described as what's called the Bronsted-Evans-Polanyi. This is an observation that you have correlations between saddle point energies and binding energies. And so, whereas you might want to, ideally you'd like a catalyst that would have weak binding and low barriers, but physics is telling you you're kind of stuck to this correlation. And the simple reason for that, at least on metals, is that both properties, binding energies and barriers, are determined largely by the energy of the d orbitals that participate in bonding. And so if you have a low energy of the d, they don't interact much. You have high barriers and weak binding. If you go to something where the d band is high, you have the opposite, low barriers and strong binding. So one nice thing about that, it's kind of frustrating because you have this correlation, and a lot of research is trying to break that correlation. But one nice thing about that is that you can reduce this sort of complex energy landscape to a simple descriptor because they're correlated. And again, this is not my work. This is Jens's, and many co-workers have pioneered this for years. And like I said, we're one of those thousands of people who use it. But you can, so for example, for ORR, have a descriptor like the binding of oxygen to the surface, or OH, or whatever. But what you can see is you get these two regimes. You get things that bind too strongly, and the activity is low because you have products stuck on the surface or intermediates. And you have weak binding where you have high barriers. And neither are ideal, and the best is something in the middle here. So platinum binds a little bit too strongly, but in terms of pure metals, that gives you the highest activity. And so, very simple model, but nice in the sense that you have a descriptor, something that you can calculate easily, and use that to try to design new catalysts or understand how catalysts function. Okay, what I've said so far really has nothing to do with electrocatalysts, and so I added this slide. Actually, I think my student Ilgar was saying I should put in something about what's come up before, but it's how you use binding as a descriptor for kinetics, or more precisely overpotentials, which is another way of, I think it's the natural way of talking about kinetics in a system. And so this example is hydrogen evolution in acid. And so it's one of the simplest reactions. You have protons in solution. They bind to the surface. And then there's a bit of a subtlety in terms of the mechanism, but in this case is, well, I think I have some description, yeah. So the Vollmer step is the binding of hydrogen to the surface, and it's electrochemical. So you combine with an electron and you get a hydrogen atom. And then, at least in some regimes, you have this Hirosky process where another proton comes and joins it, and you form H2. And so sometimes there's a kinetic barrier for that. I mean, this is not very active on gold, or weak binding, or very strong binding. It's really good on platinum. And this gives rise to one of these volcano plots. And I don't know how great this is, but this is experimental data, and you can sort of see the same trend in the binding as a function of activity. So how can we describe that? Yeah, this is strong binding and the weak binding arms of this plot. So what we can do in terms of computation, ideally we want this flat landscape. So your ideal catalyst, the binding of a hydrogen atom to the surface, would be identical to the free energy of a proton in solution, and actually identical to the free energy of your H2 in gas phase. Again, no barriers here. It's just a description based upon thermodynamics descriptors. So this would be ideal at the top of your volcano. So then if you look at platinum, which binds a little bit too strongly, what Norskov has told us is that in order for this to happen, you have to go downhill, but then you have to climb up here. So you have to apply an overpotential of, in this case, 0.1, and that changes the energy of each of these steps. Every electrochemical step gets shifted by 0.1. So this gets shifted by 0.1, and this one gets shifted by 0.2. But at an overpotential of 0.1, this becomes a downhill process, and that's when they'd say becomes active. And so that's your predicted overpotential. And so then, platinum here is on the strong binding. If you have something stronger like nickel, it binds more strongly, and so you have a higher overpotential, and this gives you the strong binding arm. The same happens for gold, but it's not climbing out of this minimum here. It's having to get over this, not a barrier, but an energy state. So this is like the OH for peroxide that Karsten mentioned. And so you have to apply an overpotential of that height in order to make this whole thing downhill. And so that gives you the weak binding arm here. And again, the activity is lower with that overpotential. So again, it's sort of a nice descriptor, but it's just based on binding energies, and the claim is that you can basically ignore the barriers, and you just want an energy landscape where it's downhill, and that gives you your overpotential when you start seeing a reaction take place. Okay, when it comes to modeling catalysts and tuning them, there's a couple of principles that we often use. So there's two here, but there's really three that I'm going to mention. So, if you have a metal surface that you want to do a reaction on and you want to modify it, one thing you can do is put that, I'm mainly talking about metals, but you could put that metal on top of a different metal. And there can be interactions between them, but one of the primary changes here is that they can have a different lattice constant. And so you can use that to change the strain in the over layer where the catalysis is happening. And so if you take something like platinum as an example I'll use, and you put it on something with a larger lattice constant like gold, you'll stretch it. And that, because you're stretching the bonds of platinum, it'll bind things more strongly. And if you put on something with a smaller lattice constant like palladium, it will compress it, and then it will become more noble. So it's a nice way of tuning the catalyst. A second way is what's called like a ligand effect, where you can put something in the subsurface, and there can be interactions between your subsurface layer and the surface layer. And there can be largely, there's electron overlap, but largely there's a charge shift. And so if you put something that will give electrons to the surface, then it's less likely to make a strong bond with something. So again, you weaken it. If you pull electrons away, it binds more strongly. So it's another nice tuning parameter. There's a third one that I'm not showing here, but you can also have a surface where it's mixed, where you have like A and B, and that's like the ensemble effect, where you can have some mix of the two, or you could even think about different reactants binding to different sites on the surface, and you can have a bifunctional catalysts like that. But those are sort of the knobs that we have for tuning. Okay, so one of the models that really got me excited about this is I think it's a fantastic synthetic technique. It was pioneered by my former collaborator, Dick Crooks. And he's able to make very well-defined nanoparticles in solution. And so basically what he does is he takes what's called a dendrimer. It's a highly branched molecule with nitrogen groups, amines at these branch points. And if you put metal salt in solution, the metal will bind to those branch points. And then you can add a reducing agent like borohydride, and the particle will reduce. And it sort of is entropically trapped in this dendrimer. So it's isolated, protected, but the very weak interaction with the surface. So if you look at the electrochemical surface area, you see all the sites. If you do UPD or stripping, you don't see an interaction from the dendrimer. And it's very well defined. Like, depending upon the generation of this, you can make a particle with 50, 100, 150, 200 atoms in a fairly narrow distribution. You can also do tricks like you can reduce one metal and then a second and make a core shell. You can reduce them together and try to make an alloy. And it's fairly flexible in terms of what metals you have, although mainly it's sort of on the right side of the D block is what you have to play with. But really nice as a model system. And another really cool thing is that you don't have to worry about support effects, because if you put these dendrimers onto a electrode, like a glassy carbon electrode here, they're close enough that you get tunneling to you don't really even see this resistance to the nanoparticle. And so you can look at the electrochemical activity without having to worry about the interaction of your particle with the support. I'm going to make an aside, I think, if I have time. Yeah. And this gets to structure. And I won't dwell on this, but it's something that I think is a potential for our community. And that is that a lot of the times we really need to know about the structure of these particles, and that can be difficult to determine, especially if you only have experiment. And I'm going to argue that if you combine experiment with calculations, you can do better. We can do better collectively. And so there's some different approaches. Like I'm thinking of a disordered material. So if you have an ordered material, you can do like X-ray diffraction or something and get a good crystal structure. But if you don't, powder X-ray gives you some information, but not a unique structure. And so this is same powder, but in a synchrotron, where you get some, a very good, what's called a PDF, a pair distribution function. And so you can learn about where all the pairs are, but this is not does not provide a unique structure. There's many structures you can get. And experimentalists will often use something like reverse Monte Carlo or something, and they end up with actually the most highest entropy structure that matches, which is not a great approximation, and that's where DFT can help, and I'll show you that. Another one, which is very powerful for this, is XSAS. It gives you short-range order. And again, it's I think there's a lot of potential for DFT to help with getting to the bottom of the structure from that. TEM is great. I mean, if you want to see individual particles, unfortunately, you can only see a few of them, and you can't do it in situ, so you have to bring your particles out, and it's a different environment, and you have this high beam which can reduce everything, and so there's some. It's powerful, and you want to use, I think, a combination, but it's not like you can just go and take your sample out and do TEM and you know what you have. I mean, you know what you have there, but you don't know that's the catalyst under reaction conditions. Okay, I'll try to be quick here, but this is some of the approaches we've used to combine calculations with experiment. And so here we've done it with empirical potentials in DFT, but I think machine learning potentials are really going to help with this. I mean, you can really sample much more space. But what we've done is we've taken these pair distribution functions, and we want to find a structure that will match that. But what we've added is a term that says we also want to get a low energy. And so it's like we have two separate things that we want to match. We want low energy, which means it's, in terms of theory, we're happy with it. We want to match experiment. And so you can think of it as a Pareto optimization, where you want to do both. And you really sort of hope for some knee in this curve. And so in this case, we defined a function that combines both of them. And this alpha says how much here if you have alpha 0, you only want to match experiment, alpha 1, you only want to match theory, but you'd like some sort of you don't know what alpha to pick, but you'd like to find some sort of knee in that curve that you're happy with both. So here's a quick example where this is one of these dendrimer encapsulated nanoparticles with platinum. And there's two FCC structures here that both match pretty well, truncated octahedron versus cube octahedron. Icosahedron you can kind of eliminate directly from, it really doesn't match the PDF. But this is that optimization where we sampled many structures and changed this value of alpha. And you can see that one structure really sort of stands out here, and that's this truncated octahedron. The lowest energy is the icosahedron, but it's way, it really doesn't match experiment. This is done with an empirical potential, EAM. This is done with DFT, but same kind of thing. Like the truncated octahedron really stands out. And that's because of a combined analysis with experimental data and DFT. The second one I'll show you is with XSAS. And this is a little more complicated. I think there's even more potential for adding our models to help understand structure. So the way XSAS works is you put in a high energy X-ray from a synchrotron, and it knocks out a core electron. And the core electron scatters off of neighbors. And it then, you get this wave here that scatters off, and it can scatter back. And if it scatters in phase, then you get constructive interference. And if it's out of phase, then it gets destructive. And so when you change the energy of that electron by changing the energy of the X-ray, you can basically scan over the neighbors. Like you can see all the constructive and destructive interference from the neighbors. And so the theory is, it's complicated, but it's also pretty simple. You kind of have the main dominant terms are the number of neighbors. If you have more neighbors, you get more scattering. You have this interference. So you have this bond length that you want to understand. And then you have a disorder, the Debye-Waller factor. If it's disordered, you don't get nice coherence. Things wash out. And so you tend to do that fitting in R space. You take a Fourier transform, and then you often take a sort of a bulk. Like let's say you're fitting a gold nanoparticle, you'd say, I know exactly what the scattering is from bulk gold, and so then I can scale it. I can adjust how many gold neighbors I have, the bond length, and the Debye-Waller factor. And if I fit that to my R space data, then I can learn, say, about the structure of the particle, how many neighbors things have, what's the disorder, and so on. It turns out that experimental fitting actually works pretty badly in many cases for disordered structures. And the reason is that you don't tend to get nice Gaussian distributed bond lengths. So this is an example with gold where you can sort of see how this is a skewed distribution. If you go to very low temperature, you start to see individual peaks at different distances. None of this is good for a bulk reference for fitting. And so we came up with what I think is a sort of clever approach in order to analyze this or test it. And that's what we can do is we can take a particle, a candidate structure, and model it with, say, DFT. So we do MD, and we can get exactly the distribution of neighbors directly from the MD. We can also simulate the XSAS, and then we can do a fit of that XSAS and compare, do we get the same distribution that you get directly from the MD? So it's a self-consistent check. There's no experiment involved there. But we can see, does the standard XS fitting tell you about the structure you know went into that data? And it turns out that very often, no. So here's an example with gold nanoparticles. And what I'm showing here is the bond length for gold. And this is XRD data. So this is pretty good. This is something we trust, and it matches what you get from DFT. But if you go and take that data and take your XSAS and fit it, you get a lower bond length when you do the fit. And you get you get a lower disorder. And so what's happening here is that in a fit that's based upon a bulk reference, you tend to think that things are smaller, more like the bulk, and more ordered, more like the bulk. It's like it's not rocket science, but you're sort of biasing it towards the model that you're fitting it to. But it's qualitatively different than what you know went into that data. Here's an even crazier example, and I'll stop at this point with this theme here, but this is some experiment where we took gold and we could titrate in thiols, and that creates a lot of disorder on the system. So, I mean, there's a lot of data here, but don't worry about it. This is this is fit to experiment. This is our theoretical modeling where there's no fit. This is just directly MD simulation and giving the excess here. And what I just want you to take home from these plots is that all of the theory or fit really match the experiment. They all look good. But if you go and look at the actual distributions, like of the first neighbor, they're really qualitatively different. So the fit from excess using a bulk reference gives you a nice Gaussian, ordered, whereas our MD gives you this big fat tail, especially when you come very disordered. And it all gets confused in the excess fitting. I mean, the bond lengths are shorter, like I said. They think it's a smaller particle. The disorder, when you fit to a bulk reference, is much less than it really is. Okay, so I'll stop with that theme. But I think there really is a lot of benefit in combining DFT and machine learning to many experimental methods. And it goes beyond this. Like right now, we're modeling like niobium oxide, which is the disordered crystal, and Raman is a very good measure of local order. But if you just do a Raman experiment, it doesn't really tell you about structure. But you can model a lot of structures and model the Raman spectra. And in some cases, you can find that it really narrows down the candidates that you could have. So anyways, let me get back to the main theme, and that is trying to design catalysts. So I'll start with an example when I was young and bold and did crazy things. Or I would never try this now, but our first sort of attempt was that if we're trying to make an ORR catalyst, platinum is the best. And my thinking was, well, let's just go to the next kind of noble metal, palladium, and we'll use our tricks of trying to tune the catalyst to make it like platinum. I mean, that'd be great. Palladium's cheaper, and I don't know. And so we thought about making this core shell particle where we could strain the surface, and we calculated these barriers and made a prediction that if you could put some very small metals as the core, then you could take palladium and compress it. It makes it more noble, makes it like platinum, should be great. So we said, yeah, molybdenum core, cobalt core. I mean, if you're an electrochemist, you're going to be, already it's like that is insane. I mean, those are not going to be stable, which is true, but we pass this to our experimental collaborators. Oh, and by the way, the thing that's sort of, I think, exciting about this sort of tuning is that you're making a structure, or ideally you're trying to make a structure that's like a noble thing, platinum, but you're making it from metals that are both less noble. So there's a lot of cheap metals out here. And so it is sort of appealing if you can use earth-abundant metals to make something that mimics platinum. I mean, that's really would be great. Yeah, it turns out it doesn't really work so well. So Keith Stevenson tried to make these molybdenum core, palladium shell, and then in TEM here, you can see the palladium formed a metallic core, and molybdenum oxide formed the shell. It's unstable. We tried with Bard. Al Bard did some work with the cobalt. It is a little higher activity when you mix cobalt and palladium, but it was not well characterized. I don't believe it has anything really to do with our calculations. So it was we were a little overly ambitious, I think. And I think that maybe just as sort of an obvious theme, I think that can happen a lot. If you just go and make predictions theoretically, this material will be great for that. You have to be able to synthesize it, and it has to be stable. And those are kind of harder things to know theoretically. And so working with experimentalists, I think, is really beneficial. Okay, so I mentioned at the very start that I'm going to talk about things that kind of work well, and then things that are a little more complicated. And this was one of our early big successes. So this is working with the Crooks group. And here we went back to a platinum shell. So that's pretty stable. And remember, platinum, so this is for ORR, and it slightly over binds. It's on the strong binding side. So ideally, you'd like to weaken the binding. And so our idea was that if you could make a core of a bimetallic, two things, gold and palladium. So gold, remember, is a bigger lattice constant. If you put gold in the core, it'll stretch it, and binding will be too strong. If you put palladium in the core, it'll compress it, binding is too weak, And so then we can just make a simple prediction where you get to the peak of the volcano. And so that's what we passed to the experimental guys. We said if you could put 75% of palladium in the core, that should be ideal. This was not an easy thing to make. I mean, they could reduce the core together, but then when they tried to reduce platinum, it would just sort of form another platinum particle next to it. And so we had to do a relatively, somewhat complicated, but they put copper on here with UPD, where you can make a monolayer, and then with galvanic exchange, we could swap it out with platinum. So they were able to make it, and kudos to them for pushing through on this. And so here's their measurements of ORR. Notice you never get better than 0.9. But if you have 50-50 in the core, you get this bad activity, and you start increasing the palladium, it gets higher activity. This is our best here. And then if you go too high, it comes back down. And so there should be some volcano here with a peak, and it is, here's their activity, and here's our prediction, and it really does work very well for the system. So it's a nice thing where properties change smoothly, we have a good descriptor, and we were able to predict this and test it. Another one sort of very quickly, this is a gas phase reaction, cyclohexene hydrogenation. Here again is sort of the energy landscapes that you get for these different steps along the way. In this case, there's really two descriptors because you need both cyclohexene to bind to the surface and hydrogen. But you can correlate these binding energies, and in this case, we did barriers as well, and correlated them with a microkinetic model. And then you can make a 2D volcano plot with your two descriptors, and where you'd like to be is at the top of this volcano. And so in collaboration with Simon Humphrey, who can make these alloy nanoparticles with a microwave synthesis method, we thought, getting to the top of this volcano, we could mix things that bind too strongly and bind things too weakly. And here we're looking at like a random alloy. So we're thinking about a surface that's going to have a mix of these two different sites. And so our prediction from our descriptors is that if you mix rhodium and silver or gold, that in some composition you should be able to get higher activity than either of them. And this turns out to work very well. Here's mixing with silver, here's mixing with gold. Here's the activity as a function of time. This is our alloy as compared to pure rhodium. Pure gold is dead, pure silver is dead. But in both cases, the alloy has a higher activity. So very nice. Okay, it doesn't always work that way, and I'll try to end with some things that are, here's a few more details. And it really comes down to the fact that you have these, rhodium binds too strongly, gold binds too weakly, and the place where you get the highest activity is in these mixed sites on the surface where you have both rhodium and gold or rhodium and silver. Okay, let me just end here with things where it hasn't worked so well. And I'm not trying to say these are good or bad. Like, I love descriptors, but sometimes it doesn't work as you expect, and then you have to sort of iterate with experiment to figure out what went wrong. And you can learn interesting things there too. So it's not like everything has to work great, and that's good. This is also interesting. But we made a prediction for a very similar system that we did before. This is this nice, stable gold palladium core with a platinum shell. And we were thinking about it for CO2 reduction. But we started just by looking at a good descriptor for that, which is CO binding, that can be measured pretty easily electrochemically. So same kind of prediction. If you have gold, you're going to have too strong binding. If you have pure palladium, it's going to be too weak. And you want to be somewhere in the middle to be like platinum, or have a tunable system. So they went and measured this. This is the stripping of CO. And at least in this regime here, it looks sort of good. I mean, in the sense that, but clearly at these endpoints, something went totally wrong. And the resolution here came both from theory and experiment. The resolution of so this is where we have a gold core and a platinum shell. So we're trying to really stretch this platinum, and we think we're going to get strong binding. And it turns out that the binding is very weak. And the resolution here was from some MD simulations where we found that our particle was just not stable. Even with a short trajectory, you just can't stretch platinum that enough and keep it stable. And so what happens instead is the gold comes up around these edges here, and the platinum forms little islands that are actually compressed on the surface. And so we went back and did EXAFs of this and found the platinum bond length, and sure enough, it was shorter. On the other side, it was the experimentalists, and they just noticed that the particle completely inverted, and the palladium just went to the surface here. And so, again, we're picturing this particle with platinum on the outside, but if palladium goes to the outside, of course, the binding is going to be much stronger. So, stability is very important, and I think working with the experimentalists is a good strategy, because all of these things are metastable, right? All of interesting catalysts are metastable. And so it's quite hard in calculations to determine what is going to be metastable enough. But in an experiment, you can just test it. So I think you want to make use of the strength of both worlds. Okay, my last example is, again, a hydrogenation, but on an alcohol. So same kind of thing. We're calculating energy landscape, descriptors, binding of alcohol, binding of hydrogen. And again, we're trying our trick that works so well with the Humphrey group, where we can combine strong binding, like palladium, rhodium, iridium, platinum, with weak binding, gold and silver. And if we mix the two, we hope for something that is high activity here for this hydrogenation. This is the experimental setup. This was Long Lu in the Crookes group who set this up. And basically, he has the alcohol here with the nanoparticles, and he feeds in hydrogen here, so that's the reactant. And then when the experiment starts, he opens up this valve here and just measures the pressure. And so if the pressure drops quickly, it's a high reaction rate. And if it drops slowly, it's low. But you can directly measure the reaction rate from the pressure. It's a cool experiment. So in some cases, I'll start with the one that doesn't work here, and that is when you mix platinum and gold. So our idea here was that if you mix this strong binding and weak binding metal, platinum and gold, there should be some composition where you get high activity here. That is not what we see. As a function of so here's the experiment. Here's the pressure dropping. And if you have pure platinum, it drops at this rate. And then if you start adding gold, it just gets worse until you get no activity with pure gold. And so basically the activity is really just correlated with the amount of platinum. There's no beneficial effect there, strangely for us. I mean, that was our prediction. With palladium, it actually looks pretty good in the sense that here's pure palladium. When you start adding gold, the activity goes up and then goes down, and you get this kind of volcano that we were expecting. But that was very odd to us, because I think of platinum and palladium as pretty similar. I mean, they're right next to each other on the periodic table, and I mean, they're a little bit different, but I wouldn't expect, and it's a qualitative difference in terms of how the alloy is functioning. So the resolution here, it actually, we could see it in the calculations when we did it. This is looking at our descriptor, the binding energy of hydrogen as a function of composition. And if you look at a palladium alloy, you see a nice tuning of the binding energy. That's what you need for high activity. For rhodium, it's kind of not linear. You get this curved. But here's the worst, is platinum. So here's the binding of just gold. It's weak. But as soon as there's any platinum, it just goes to a constant. There's no sort of tunability, which is very unusual. But you can actually see it in these pictures here. I think I've blown them up. Yeah. So here's hydrogen binding to this palladium gold alloy. And here it's pure palladium. And so the hydrogen is feeling the binding of 3 palladium atoms in a hollow. And then as you start to add gold, it gets weaker and weaker and weaker. So you get this nice tunability. With platinum, sort of remarkably, it doesn't do that. So here it's binding to a hollow site with platinum atoms around. But then when you put gold in, it just moves over to a bridge site. And when you put more gold, it moves to a top site. And so everything is like binding to platinum. That's this flat region here. And it's only when you force it to be purely on gold does it jump up to the binding of gold. And you don't get anything here in the region where you'd like it to be. where it's in the intermediate. We actually don't really understand what's different still at a fundamental level. We've tried, but I don't know. We see it in our calculations. And actually, I think this is the nicest part of this story, is that we were able to then go back and validate this. So we did, what we did is grand canonical calculations of hydrogen binding. And you can see that on the platinum case, it's just a linear trend. The amount of hydrogen you get on the surface in experimental conditions just goes with the amount of platinum. And that's where the activity goes. The palladium is quadratic because you not only have more palladium when you add it, but also you weaken the binding. And so those two effects basically multiply and you get a quadratic. But that's a prediction that we could pass to the experimentalists, and they did electrochemical stripping of hydrogen, and they could integrate under these peaks here. It's a little, I'm not quite sure. I mean, those don't look like really well-defined peaks, but somehow they integrated that, this hydride wave, and then they could see how much hydrogen was on the surface on these different particles. And like we predicted here, linear trend with platinum, quadratic, a tunable effect with palladium. So I think that was a nice validation. Okay, with that, I think I will basically stop. I mean, this is sort of just reiterating the point that with palladium, you can tune and you get across the volcano plot. With platinum and rhodium, you basically are stuck at strong binding, and then you have to, you jump to weak binding or vice versa. But you never get near you can't tune it near the volcano plot, near the peak of the volcano. I think I've made these points. I'll just stop here and thank the group and thank you for your attention and bearing with me, not addressing any of the key topics of the program. But anyways, that's the kind of, that's the kind of our approach in what we do. So thank you.